Hi everyone. In this lecture, we are going to talk about the power cycle, which uses gas as a working fluid. This cycle is called a gas power cycle. In this part, we'll start with an ideal gas power cycle called the Brayton cycle. Now, let's get to know an ideal gas power cycle. The Brayton cycle is the air standard ideal cycle approximation for the gas turbine engine. The simple diagram of a gas turbine engine is shown here. The gas turbine engine is an open system. This engine is used to generate shaft work or electricity by burning fuel with compressed air. The engine consists of three main pieces of equipment, which are compressor, a combustion chamber, and a turbine. Firstly, fresh air is drawn into the compressor. The air will be compressed from atmospheric pressure to a higher pressure, which is process 1-2. It will be used to burn fuel in the combustion chamber. The chemical energy from fuel will be turned into heat energy. The flue gas obtained from the chamber will be at a higher temperature and pressure. This gas, at point 3, has a high potential to produce work. It is then expanded through the turbine to produce work. The turbine and compressor are connected to each other via a single shaft. Some amount of shaft work produced from the turbine will be used to drive the compressor. The remaining work or net work output will be used to generate electricity. The exhaust gas from the turbine will be released and cooled down in atmosphere. We can see that the gas turbine engine does not operate in a cyclic manner. The composition of the working fluid flowing through each equipment in the engine is also changed, which is from fresh air into flue gas. Some assumptions are therefore needed to simplify the gas turbine engine into an ideal gas power cycle. The assumptions that we have to make to simplify our analysis of the gas turbine cycle are called air standard assumptions. For the first assumption, the working fluid is assumed to be just air, which continuously circulates in a closed loop and always behaves as an ideal gas. It means that the working fluid will have no composition change as it flows along the cycle. Next, the combustion process is replaced by a heat addition process from an external source, which is equivalent to the chemical energy released from the fuel combustion. However, the amount of fuel required in the combustion is normally insignificant when compared to the airflow. We can then neglect the amount of fuel flow and assume that the airflow is constant through the combustion chamber. If you take a look at the figures on the right-hand side, the actual combustion is in figure A, but the ideal combustion is on figure B. The next assumption is that all processes that make up the cycle are reversible, which makes the cycle internally reversible. To close the cycle, instead of releasing the exhaust gas to atmosphere, the exhaust gas from the turbine, which is now assumed to be air, will be cooled down in a heat exchanger and then put back into the compressor again. Finally, the air properties are assumed to be constant anywhere in the cycle, although the air temperature varies significantly as it flows through each equipment. The specific heat capacity of air is assumed to be constant at room temperature, which is around 25 degrees Celsius or 77 degrees Fahrenheit. This is called the cold air standard assumption. As a result, when applying the cold air standard assumptions to the gas turbine cycle, it becomes a closed-loop gas turbine cycle or Brayton cycle as shown here. The cycle consists of 4 reversible processes, which are 2 isobaric and 2 isentropic processes. The first step is an isentropic compression in a compressor or process 1-2. The next step is an isobaric heat addition in combustion chamber or process 2-3. P2 is equal to P3. In this step, unlike the Carnot cycle, the process heat addition is carried out at constant pressure, which is easier to operate and more practical than the isothermal process in the Carnot cycle. The temperature along the process change is allowed to increase. So we have T3 greater than T2. The flue gas exiting the combustion chamber is then expanded isentropically through a turbine or process 3-4. Finally, the exhaust gas from the turbine is cooled down in a cooler and then returned to the compressor to complete the cycle or in process 4-1. In this process, it is also an isobaric process, and we will have P1 equal to P4. Now, let's have a look at this cycle on TS and PV diagrams. You can see that the first step, which is isentropic compression, on the TS diagram, the process will change in a vertical direction from point 1 to point 2. After that, when it undergoes an isobaric heat addition, it will follow a constant pressure line or isobar. So we have a temperature increase from point 2 to point 3. The flue gas, when it exits the combustion chamber, will expand isentropically through a turbine. After that, it will follow another isobar to cool down and complete the cycle at point 1 again. You can see that the shape of the cycle on TS diagram is different from what we have seen in Carnot cycle, which is only a simple rectangle shape. But in Brayton cycle, the shape of the cycle on TS diagram is a skew rectangle. On PV diagram, the process starts at point 1, then follows an isentropic line to point 2. After that, it moves along a horizontal direction in an isobaric heat addition to point 3. Then, another isentropic expansion as in process 3-4. And finally, closing the cycle with isobaric heat rejection in process 4-1, as shown in another horizontal line on the PV diagram. We can calculate the thermal efficiency of the Brayton cycle using the same concept that we have learned before, which is what we get divided by what we give. For the power cycle, what we get will be the net work output, and what we give will be the heat input. From the energy balance, we can write the thermal efficiency as 1 minus Q out over Q in, as shown in this yellow box here. Now, we will try to write the efficiency in terms of temperatures as we have done in Carnot. So it means that we have to write Q out and Q in as a function of temperatures. To do this, we have to do the energy balances in process 2-3 and in process 4-1 to get Q in and Q out. We start the process 2-3 to determine Q in. from the energy balance at steady flow and neglecting changes in kinetics and potential energies. We have energy flowing in must be equal to energy flowing out. So we have energy flowing in with the feed plus heat supplied to the combustion chamber must be equal to energy flowing out with the gas products. Now, from the conservation of mass, we have single inlet to and single outlet from the combustion chamber. It means M2 equals to M3 and equals to M dot here. Substituting M dot into the energy balance equation, we have Q in equals to M dot multiplied by H3 minus H2. For gas enthalpy, if we apply constant specific heat or as standard assumption, the enthalpy change between inlet and outlet can be written as Cp multiplied by T3 minus T2. We can then write the heat transfer rate as a specific heat rate or small q in here. This is equal to q in divided by m dot, which is equal to Cp multiplied by T3 minus T2. We can also set up an equation to calculate Q out by doing energy balance around process 4.1. The balance equation will be similar to what we get earlier from process 2.3. Here, we'll have Q out equals to Cp multiplied by T4 minus T1. Now, we can substitute Q out and Q in back into the efficiency equation. So we'll have the Brayton efficiency equals to 1 minus Cp multiplied by T4 minus T1 divided by Cp multiplied by T3 minus T2. From the cold air standard assumption, Cp value is constant and can be cancelled out. The Brayton efficiency can therefore be reduced to 1 minus T4 minus T1 divided by T3 minus T2. We can then make some adjustments with the term in the brackets by pulling T1 out of the top bracket and pulling T2 out of the bottom bracket. The Brayton efficiency will be written as shown here. You can now see two temperature ratios inside both brackets, which are T4 over T1 and T3 over T2. We are going to find out how both of them are related to each other. We take a look at the isentropic relationship in process 1.2 and 3.4. We have a relationship between temperature ratio and pressure ratio as follows. The temperature ratio will be equal to the pressure ratio to the power of K minus 1 over K. In this case, K equals to heat capacity ratio or Cp over Cv. For air, K value would be 1.4. You can find this property in the appendix of most thermodynamics textbook. For process 1.2, we will have T2 over T1 equal to P2 over P1 to the power of K minus 1 over K. Similarly, for process 3.4, we will have T3 over T4 equals to P3 over P4 to the power of K minus 1 over K. Now, from the isobaric processes, we know that P3 equal to P2 and P4 equal to P1. Therefore, the terms on the pressure ratio on the right-hand side of both isentropic equations are equal. We then have equal temperature ratios from both isentropic processes, or T2 over T1 equals to T3 over T4. By exchanging the terms T2 and T4, we have T4 over T1 equals to T3 over T2. Now we get what we are looking for, since the temperature ratio in the top and the bottom brackets from the equation in the previous slide are equals. The terms in the top and bottom brackets can be cancelled out. The Brayton efficiency equation can then be reduced into a very simple form, which is 1 minus T1 over T2. This form looks pretty much like what we have found in the Carnot efficiency equation, which is 1 minus TL over TH. They look so similar, but are they actually the same? We'll see if they are different or not in the next slide. In this slide, we'll take a look at the difference between Carnot and Brayton efficiency. Let's have a look at both cycles on TS diagram, starting with a simple Brayton cycle shown here. The area inside the cycle represents the net work output. When we compare this cycle with the Carnot cycle operating between the same maximum and minimum temperature range, Carnot cycle will be enclosed with this simple rectangle operating between T3 and T1. So you can see that the area from the Carnot cycle is much larger than that from the Brayton cycle. Now, if you compare them in terms of the efficiency equations, you see that the Brayton efficiency equal to 1 minus T1 over T2, while the Carnot efficiency is 1 minus T1 over T3. So the Carnot efficiency is always greater than the Brayton efficiency. The forms of both equations look very similar, but actually they are different in terms of the temperature of the heat source. We can also write the Brayton efficiency in terms of the pressure ratio as well. We have the isentropic relationship between the temperature ratio and the pressure ratio as shown here. We can then replace T1 over T2 with the terms of pressure ratio in the Brayton efficiency equation. The result would be 1 minus 1 over pressure ratio to the power of K minus 1 over K, as shown in this yellow box here. Now, if you plot the Brayton efficiency with the pressure ratio, you can see that the curve will be nonlinear as a result of the power law relation. From the graph, you can see that the Brayton efficiency increases as increasing the pressure ratio. The typical pressure ratio values that we normally use in practice will be in range of 5 to 20. Now, that is the end of this part. We'll have a look at a calculation example on how to analyze the performance of a Brayton cycle in the next video clip. Thank you for watching. Goodbye.